The only series that we've looked at considering the sum of would be a geometric series where the common ratio was greater than 0 or less than 1. So until now, we really weren't interested in the sum of the series. We were just interested in whether the series converged or diverged. But we do know that if you are asked to find the sum of a series, that they're pretty much telling you, well, that series has got to be geometric, because that's the only type of series that we know how to find the sum for. It's the only series that we have a formula for. Okay, and that still continues to hold true. Okay, but with regard to the alternating series, okay, we do have a certain situation where we can approximate the sum of the series. Okay, so let's look at the alternating series remainder. And this actually is a theorem that's provided for us, and it's on page, let's see, 633, and it's kind of interesting to read. Okay, this is saying that if a convergent alternating series satisfies the condition 2 of our test, then the absolute value of the remainder, okay, now think about this for just a second, the remainder of n terms, the absolute value of the remainder involved in approximating the sum of the series by a partial sum, okay, is equal to or less than the first neglected term. Okay, I know that's a lot, but what this is saying is S represents the sum of the infinite series, whatever that is. Okay, let's say I choose to take the first 10 terms, the 10th partial sum, S sub 10, okay, and I take that and I subtract it from whatever is the sum of the series. Well, we call that the remainder. Okay, the R sub 10, if that's what I've chosen. Okay, and what we're saying is that remainder is going to be less than or equal to the first neglected term of all the terms that I'm using to create the nth partial sum. Whew. Let's just see what that looks like in an example. Let's approximate the sum of this alternating series by its first 6 terms. Okay, so we're going to have to generate 6 of them and look at the 7th one. All right, if n is 1, let's see what happens. Then we have an even exponent, and so our first term is going to be positive. So 1 over 1 factorial is just 1. Then it's going to be minus. Okay, if n is 2, that exponent's odd, so that's why that's negative. That's 2. It's 1 over 2 factorial. Got it. Okay, I'm using the first 6 terms. Got it. 1, 2, 3, 4, 5. This is the first 6 terms. Okay, but in that whole long thing I read just a minute ago, it said something about the first neglected term. So I'm going to go ahead and generate 7 terms. Generate one more term than you're asked to use to approximate the sum. So there we go. Okay. Of course, I'm going to take a calculator. If I'm approximating the sum by these first 6 terms, okay, that's my S sub 6. I'm going to use a calculator. And the calculator gives 91 over 144. Which, if you wanted to change it to a decimal, that might have a little more meaning for what we're going to do next. Okay, so the first 6 terms added up give us 0.63194. Okay, and what this alternating series remainder, this theorem tells us is, okay, that the sum of the series is S. I don't know what it is, but it's going to be close to this, especially if I just keep alternating signs of smaller and smaller numbers. It's not going to grow by much. Okay, the sum minus S sub 6, this value, right here, is equal to what we call the remainder, using the 6th term, right there. And then that remainder is going to be less than or equal to the 7th term, the first neglected term, which that term is 1 over 7 factorial, and that is actually 1 over 5,040. Okay, so we're not quite done. We haven't really fulfilled what they want us to do. Approximate the sum by its first 6 terms. So this is the remainder, or this is the 7th term right here. So we know the remainder is going to be less than this value. Okay, so to finish this up, we're going to create an inequality. Right, I'm going to take the 6th partial sum, and I'm going to add and subtract this remainder and create an inequality. Okay. So the sum of the series is going to be in between these two values I'm creating. And actually 1 over 5040 is a decimal. It's 0.0002. That's what these are, this is equal to. Okay. So I'm going to, actually I'm going to, yeah, right here, I need the space. The sum of the series is greater than or equal to, when I subtract 0.0002 from this, I'm going to get 0.63174. So my sum's got to fall in between these two numbers where I take the partial sum and I add or subtract the first neglected term. So if I added 0.0002, ooh, that's going to go up a little bit. It's 0.63214. Okay, if you think about it, the sum of the series to fall in between these two numbers that are already close to the thousandths, okay, gosh, that's a pretty good partial sum to estimate or approximate the sum. Okay, let's look at another example. Again, let's approximate the sum by its first 6 terms. So let's generate those first 6 terms. All right, so generating the first 7 terms, and then plus dot, dot, dot. So what I want to do is I want to find the 6th partial sum. So adding the first 6 terms, 1, 2, 3, 4, 5, 6, right? I get 0.1875. So next I'm going to get a boundary and inequality for my sum. So, oh gosh. Okay, now we're going to start all over. Right, and that's so much better. Okay, so yeah, the sum of the series S minus the 6th partial sum, or whatever we're finding, is equal to the remainder. And that's going to be less than or equal to the 7th term, okay, which is equal to 7 over 128. .05469. Okay, so let's set up our inequality. Okay, so the sum of the series is going to fall between this number subtracted by the value of the 7th term and the 6th partial sum increased by this right here. So I'm actually looking at the solution manual coming up with these answers, but I think it'd be best if we had more decimals than what the solution manual provides. But for this and what we're doing right now, I'm just going to report this. Okay, if we wanted to get a more accurate interval for our sum, then we would just have to find more than the 6th partial sum. Okay, but for right now, that's good. Okay, we're within hundredths, or I guess tenths. So that's pretty good of the sum of the series. So that's using the alternating series remainder. I'm not sure if your worksheet has this last information that's on the back here or not. I think it still does, but I can tell you that College Board does not require that we look at absolute convergence. So anywhere from here on down, woo, let's just cross that all off. Okay, we've done what we needed to do for the alternating series test and the alternating series remainder.